This presentation has been prepared as a pre-presentation for the International Conference on Dark Matter and Dark Energy taking place in Amsterdam on November the 5th and 6th. And the topic of this presentation is the explanation for dark matter and dark energy. In this paper presented at the conference, I will be explaining that to get to the bottom of this mystery about dark matter and dark energy, we actually have to change our fundamental understanding of the evolution of the universe. In fact, we have to discard the Big Bang theory and look for an alternative. Now, what first convinced me that the Big Bang theory was wrong was looking about 15 years ago. I found that the data from NASA was generally available. The availability of galaxy position data could be downloaded by anyone. You didn't need to be a researcher. You could just go online to the NASA extragalactic database and download the data for the positions of galaxies. And as a personal interest, I did this, and I thought it would be interesting to look at the distribution for patterns. And what I found was that the distribution of galaxies was completely inconsistent with the Big Bang theory, in the sense that if you look at the number of galaxies by distance, you find that there's a very tight grouping for the evolution of this curve, and convinced me that there had to be an alternative to the Big Bang theory. So why should we look for an alternative? Well, firstly, we've been unable to explain dark matter and dark energy. Then it's clear that the Big Bang theory does not conform to the law of conservation of energy. And more, with more ability to analyze what we're seeing in the universe, it's becoming clear that there are objects such as stars and globular clusters which are older than 13.8 billion years, which is the age of the universe as determined by the Big Bang theory. So it makes no sense to have objects within the universe which are older than the universe itself. So having developed an alternative to the Big Bang theory, which I'll be presenting here in this presentation, it then becomes clear which of the assumptions of the Big Bang theory are in fact false. And they're listed here, the three assumptions which are not correct. And the point to emphasize here is that these are assumptions. Now, the Big Bang theory says we look at all these galaxies and we go back in time, and the galaxies get closer and closer together and the universe gets hotter and hotter. And the implicit assumption is that all that matter, when we go back in time, all that matter formed at one time. The cosmological principle is that we're not in any special place in the universe. We've been caught out like this before. We thought we were special, and that the universe looks the same wherever you are. It's got the same physical properties and looks the same in all directions. The physical properties are the same, but it turns out we are in a rather particular place, quite close to the center of a finite universe, which I'll come to. And then the explanation from for the cosmic microwave background radiation, which is the key element which convinced everyone that the Big Bang theory was right and the steady state theory was wrong, was the cosmic microwave background radiation, which it's claimed is the echo of the Big Bang coming from recombination. So this slide shows an illustration of the hot Big Bang model, and you can see on the right we've got today, inside the blue circle, we've got around 1 trillion galaxies with an estimated mass of 10 to the 54 kilograms. So we're talking about 10 to the 12 galaxies, each of which is around 10 to the 42 in mass. And that mass, the hot Big Bang model says you take that back in time, and all that matter already exists in a tiny volume the size of a grapefruit. So if we don't like the Big Bang theory, and if we've got grave doubts about that, let's go back to very first principles and start thinking about what the nature of the universe would be. And there are actually 3 possibilities in terms of finite and infinite. So we could assume that the universe was infinite, or we could assume that it's finite without a boundary. So these first 2 points are what people would usually argue between. Some say it's infinite, some say it's finite, but with no boundary. What this proposal is saying is that we have to look at the case where we think of the universe as finite with a space boundary. And for very good reason. An infinite universe would require infinite energy. And if the universe was finite with no boundary, then that means it curves back on itself. And studies of the cosmic microwave background radiation show that in the radial direction, the universe is completely flat. So that rules out that possibility. So here in slide 5, we can, once we've taken the point that we have a universe which is finite with a boundary, that implies that the universe has a center. And it also implies a rest frame. And we have observed a rest frame, which is the cosmic microwave background rest frame. And we can measure the speed of the Milky Way galaxy relative to this rest frame. And using Hubble's law, we can then fix our position relative to the center of the universe. So you can think of this model of the universe as being a space where all galaxies are moving away from the center of the universe due to the expansion of space. And individually, each galaxy will also move under whatever gravitational effect it is subjected to. And from using this observational data, we find that the Milky Way galaxy is around 26 million light years from the center of the universe, which puts us quite close to the center of the galaxy distribution. And this explains why the galaxy distribution seems similar in all directions. and explains why we might have come to the conclusion that the cosmological principle is true. But in fact, in a finite universe, the cosmological principle must be false because the position close to the boundary is clearly different from the position close to the center. So we said in the Big Bang Theory that it violates the law of conservation of energy. So let's think about how we can develop a theory which conforms to the law of conservation of energy. And our thoughts about conservation of energy have changed over the years. We used to think that mass was conserved. We used to think of energy being conserved, and we thought of these as being completely independent. But with E equals mc squared, it's clear that mass energy is conserved, and mass can be converted into energy. What this slide tells us, and what general relativity tells us, is that you have to generalize, again, your conservation of energy law to make total energy equal to mass plus energy plus space-time curvature. And this equation that I'm showing here is just the Einstein equations reorganized a little bit to say mass plus energy plus space-time curvature is 0. And in this equation, mass is always positive, energy is always positive, and space-time curvature is always negative. And so with this in mind, you can see that to balance the energy equation, the space-time curvature contribution has the ability to provide the energy for matter formation. So we'll start with the simplest idea. We'll start with a spherical region of empty space with a space boundary. We'll assume that the universe expands at a constant rate, and we can measure this rate directly because we can observe the expansion of the universe and measure it fairly accurately. And I tend to use an expansion rate which is 1 part in 14 billion light years per year per light year. And that would correspond to 69.84 kilometers per second per megaparsec, which is the units that astronomers tend to use. And in this model, to balance the total equation, we need matter formation. And the matter formation is not at some initial beginning of things. It happens as a result of galaxy formation events over an extended period of time. Slide 8. So now we're going to look at the expansion of the universe, and using some fairly straightforward mathematics, it becomes clear that if we're assuming that the expansion of every segment of space is the same, then if we take the radius of the universe, the expansion of the universe by simple integration produces an exponential relationship between the radius r and the time t. And I find it very convenient to work with r in light years and the time in years. And from this formula, it tells us that the radius of the universe increases by a factor of around 2.7 every 14 billion years. So let's think a bit more about this process of matter formation in the universe. We're going to make a couple of assumptions here, which seem reasonable, that the matter generation capacity of each unit volume in the universe is the same. So the total mass in the universe, we can assume, will be proportional to the total volume of the universe. And we can tell from observations that the average matter density in the universe is something of the order of 1 hydrogen atom per cubic meter. Now, if the volume of the universe increases by e to the power 3, so we're talking about a volume expansion derived from a linear expansion, so we cube the expansion rate to get a volume expansion of around 20, a factor of 20 every 14 billion years. So this tells us that the total mass in the universe in the form of galaxies will increase by a factor of 20 every 14 billion years. And so this gives us an estimated time since the first galaxy formed of 126, which is 14 times 9. And that number 9 comes from the observation that we're taking a rough ballpark estimate of 20 to the power 9 galaxies, which is 500 billion. So these are just ballpark figures, but you can see that we're going way beyond the 13.8 billion years age of the universe that is currently proposed. And this is how the position of galaxy formation evolves. We have in slide 10, the first galaxy forms. 14 billion years later, we have 20 galaxies. 14 billion years after that, we have 400 galaxies, and so on. Now, the position of galaxy formation moves outwards towards the boundary. And in fact, most of the galaxy formation today is going on beyond 14 billion years. You can deduce this from the model. And that explains why we don't see directly a large amount of current galaxy formation. What we do see very occasionally at distances of 6–10 billion light years is huge gamma ray bursts, which no one can believe are a single multi-directional event. They would assume that it must be a jet because it's so energetic, it outshines the entire universe. And what those distant gamma ray bursts are, I would claim, is a galaxy formation event, because what the energy that's being released is of the order of 10 to the 42 kilograms to form the mass of the new galaxy. And what we're observing in the gamma rays is the energy that has not been converted into matter. So we need to tackle this thorny question of what is the cosmic microwave background radiation, because it can't be what the Big Bang Theory thinks it is, which is an echo of the Big Bang. And by analyzing this problem, it's very clear that you can use the Schwarzschild solution to estimate the existence of an event horizon at a distance which must have been at 8.77 billion light years from the center at a time 13.8 billion years ago. Now, we've been used to using the Schwarzschild radius calculation for black holes. And indeed, though it proves very accurate, and we always think of an event horizon as being viewed from the outside, or not viewed at all because it's a black hole, we don't see anything. But the mathematical equations show that the event horizon effectively produces a demarcation or a threshold or a boundary, in a way, between the region inside the event horizon and the region outside the event horizon. But the region inside the event horizon is space-time. And the equations are general, and even though we've previously applied them to black holes, which are a very small, dense distribution, there's absolutely no reason why the same equations can't be applied to a distribution of matter, which is very low density, which results in a very large Schwarzschild radius. And it turns out that the density required to produce an event horizon at 8.77 billion light years is about 0.724 hydrogen atoms per cubic meter. So here's an illustration of the various horizons and boundaries that that we understand. So the space boundary is shown as the outer black dotted circle in this diagram. The observation horizon is at a distance of 14 billion years, centered on the observer, but because we as an observer are quite close to the center of the universe, we can take all of these circles as being concentric. And finally, the event horizon is, or I should say was, at 8.77 billion light years at a time 13.8 billion years ago. And you can see that light coming from just within the event horizon, even though it was at 8.77 billion light years, would take 13.8 billion years to reach us because of the expansion of space. And this relationship between the time and the expansion, it can be calculated, and this is referenced in the paper. So what I believe is happening is that the galaxy formation starts close to the center, moves outwards, and eventually there's enough galaxies to form an event horizon. And at that point, any galaxies within the event horizon will be subject to the expansion of space, but they certainly can't cross the event horizon. So the hypothesis is that there will be a buildup of galaxies, almost like a shell of galaxies, just inside the event horizon by this process. And the proposal then, and this needs a lot of work to convince me and everyone else that this is the correct assumption, that the cosmic microwave background radiation is coming from this distant field of galaxies. And over time, the temperature of the radiation will cool from the heat of the galaxy down to the observed cosmic microwave background. So although I say I'm not 100% sure of the exact source, what is clear is that there will be an event horizon there, and the cosmic microwave background is consistent with radiation coming from a source just inside the event horizon. So now we come down to, following all this preamble, we've been saying, well, we're going to explain dark matter and we're going to explain dark energy. Let's get down to that topic. So the proposal is that a galaxy formation event, the release of energy from space-time, creates a huge wave disturbance, and ultimately there are very few stable particles, and what is formed, in fact, perhaps from a spiral wave, a series of neutrons with a shared axis of rotation. And these can pair up and bond to form dineutrons, and that's the proposed dark matter particle. So there we have the search for the dark matter particle is over, and many people have said, well, it couldn't be baryonic because we've looked at all of the particles of the standard model and none of them meet the criteria. But no one has actually sat down and said, well, maybe it's a pair of particles or a bonded particle, and that's really what is the proposed solution. So from the neutrons we get dark matter and single neutrons. Some don't pair, and before they can pair, they form a proton and an electron through the normal decay process that we're familiar with. That leads to hydrogen atoms and hydrogen molecules. And you can also see that if you had a dineutron which captured a proton, or then in fact captured two protons, then you'd find you've got a nucleus of two protons and two neutrons, and then an outer shell of two electrons, and you've got a helium atom. So this can explain the production of helium right at the galaxy formation event. And then all of this matter can accelerate towards the center. At the same time, the whole halo, the whole spherical region is expanding, partly from the explosion and partly from the expansion of space. And so the gravitational acceleration affects mostly the matter close to the center, which collapses down to the center, and typically 1/1000th of the total mass of the galaxy can condense into the center and form a massive neutron star, which we observe as a black hole. Finally, we come to dark energy, and we have to really go back to what was observed, because what was observed and led to the concept of dark energy was the unexpected recession velocity of distant galaxies. And because of that, the conclusion was taken, well, oh, in that case, we're looking at galaxies which were there many, many years into the past, and therefore the universe expansion must be accelerating. But that's not the case. What's happening is that these distant galaxies are affected by the gravitational acceleration due to the distribution of galaxies located closer to the center of the universe. So as well as an expansion component, there is an acceleration towards the center of the universe. And this component is what is causing the unexpected recession velocity of the distant galaxies. So dark energy is not real. the expansion of space is not accelerating, and the effect is caused by our misunderstanding of the fundamentals of cosmology.